이제 갈 거니까. In this, we call this boundaries. In matrix, a lot of objects are floating around this space. This is space in the matrix, and there are objects on the space, and we put phi of 0, and we Q. We have the boundaries of time and space on its own called the conformal boundaries. Conformal boundaries, and they are supporting the laws of time that was mentioned by Newton. To finish this equation, we will write wave function n right here, because we need the wave function t and wave function times wave function t and wave function. That's 5. That looks like 5. This may look like 1, but it is inside a big bracket, which is meaning that it is similar to emitters. When the phi of 0 is equal to the matrix of the conformal boundaries, which means that the conformal boundary is inside the rows of matrix and space, this equation comes out like this. Yes. And when this equation comes out as half calculated, and my equation this must be wait a minute, DK. Bigger than sigma T1 and T2 equals 0, and that's over 1. The little space. Of course, we have the theta, and exchanging the values of deltas. This a little energy repulsion. this is my equation. It is not as simple as this equation, but this is meaning this equation breaks everything, even space itself that is containing an infinite value of conformal boundaries inside the matrix mechanics, which was made by Werner Heisenberg. But in matrix mechanics, conformal boundaries are really important, even though he never cited it. Conformal boundaries go in matrix mechanics as two barriers. When conformal boundary is like this and another one is like this, matrix, and four matrices inside the conformal boundaries, and when we put that in the infinite value, then a circle comes out, and that is called the block sphere, which was made by Werner Heisenberg, okay, because he's a genius. He made matrix mechanics, principle of uncertainty, and he made block sphere, and he found conformal boundaries, Werner Heisenberg, because he's a genius. And in matrix mechanics, conformal boundaries, Werner Heisenberg stated that the volume of the conformal boundaries can never be calculated. But then, in 1929, Paul Dirac calculated and proved Werner Heisenberg wrong, which made Werner Heisenberg angry. That made his development of finding of the conformal boundary. When those two fought and did their fightings, even though Paul Dirac didn't even fight and just calculated, in those, Paul Dirac thought that the volume of conformal boundaries are different thing, the volume that Paul Dirac calculated was different from Werner Heisenberg's calculation of the conformal boundaries. So they fought, even though Paul Dirac didn't fight. When they fought, I think, and this is the volume I calculated, which is same as Paul Dirac. So which means that I did the work of Paul Dirac. But then, see, Paul Dirac calculated this even though he never announced it, so it's not famous as Werner Heisenberg. So everybody thought that Werner Heisenberg was the first one to find conformal boundaries and make his own theory and even make a solution for it. But actually Paul Dirac did it, even though we still don't know who is right. But I think Paul Dirac is right, because I got the same value as Paul Dirac. And this equation that I made is delta x as delta is, so in conformal boundaries, most of the things go like this. Everything goes like that, except electrons and photons. This space right here, this space is where electrons and photons go fast. This is very weird in physics and unknown, but when a particle is in a vast space alone, and when it goes down and inside to a small pit, it goes faster, and then it releases to the opposite side. That is what is happening to the electrons and the photons in there. Electrons go here, slowly, photons go here, slowly, even faster than electrons. But I've said that most of the thing go like this. But when an electron or a photon goes like this, and this, it's weird, and this is the direction where time goes. So time goes on like this, and for electrons and photons, they are experiencing at right in this way. So I will draw. It looks like this. It's a diagram actually, and so this is a diagram of an electron. Which makes the value of this is the diagram that I made. And this is the equation. I mean, this is the calculation for what is in here. See? And this is, right now, this is the space where this is. This is where electrons are traveling very fast, almost faster than the speed of light, even though that is not that fast. So in here, electrons are experiencing something like a time. There's no time for them. They're going opposite of time. Electrons are breaking time. Small electrons are breaking big times. Time is big and time goes on forever, infinite, ticking all the way. And electrons, they are breaking time. They are breaking the value of infinity. So it doesn't make sense. The electrons don't make sense. But electrons inside us. That means we're breaking time. If we go to space, we break time. That means astronauts break time. It's weird. So I made this. And this explains that. Why it's breaking time. Why it's breaking time is because it is happening inside the conformal boundaries. This equation, this formula, when a space is like this formula, conformal boundaries are floating over the space, and when it floats, the space curves. It should be straight. But in general relativity, in the orbit, it curves through Earth, and there's a curve, like a pit, for the sun to go, and then there's the Earth. But then that is it happening same as conformal boundaries, which shouldn't be happening. Conformal boundary is inside the space, and it shouldn't curve. It should be hard. But then curving like this. There's a pit, a small pit for conformal boundaries. Like a den for a dog. That is happening to conformal boundaries. It's inside the matrix, but it's folding. The matrix is folding like a dog's den, like a cave. So this pit that is inside the matrix is breaking time. Underneath the matrix is another conformal boundaries. But then when a conformal boundary pushes, the pit goes away. It's hard now, and we can't break it. Unless another conformal boundary from any other side comes and breaks it. Because when there are two is bigger than one, so that means two can win one. by beating one and make a pit again. And one will go away. And there will be two, which make a big pit. They go. Then bigger than, like a cake. And so when there are infinite value of conformal boundary, inside the matrix is the abyss. Abyss. We can't measure it because it's so deep. It's infinite. So it's B infinity, not B1, B2, basement 3. It's not like that. It's basement infinity. We're going down infinity. The value of infinity. Infinite floors going down. Not going up, but down. And that pressure is causing the volume to decrease, which made the difference between Werner Heisenberg and Paul Dirac's calculation of conformal boundaries. Werner Heisenberg didn't minus the abyss, the volume decreasing by the pressure, because he didn't know how to. But Paul Dirac knew how to, because he learned math properly. And I call this delta x, and the value is coming out as t1 and t2 equals 0, and well, my equation is right here. So this is two exchange, and you have RS that is bigger than 1, and we have the value of pi.
네, 나중에 어느 대학교에서 보여달라고 할 수도 있는데 그렇게 펄트 하면
계속 맞아 안돼 이거.
이건 너무 2급 비밀 서류 그 영상 아니냐? 너무 계속 펄트하는 거 아니야?
그 와이프한테 하고 해줄 거야.
와이프는 그나마 낫지. 너 나중에 대학교에 이런 거 서류 다 필요해가지고 제출할
끝나잖아
때.
그냥.
아니 뭐 이론만 좋으면 그 정도 펄트야. 그냥 웃기고 말겠지.
아니야 안 보여줄 거야.
이거 다 기록이야. 나중에 너한테 다. 빨리 해. 엄마 편집해줄게 나중에.
The exchanging value is here. It's right here and here. That is the exchanging value that are just in the vertices. And here is the specific sigma. This equation shows the phi of. Do you know what phi is? Phi is this. Okay? Phi. And do you know what's this? Psi. And do you know what's this? Theta. Okay? And do you know what's this? Mu.